Welcome back to COMP526 efficient algorithms. In Unit 3, we'll talk about sorting and a little bit about divide and conquer beyond sorting as well. The learning outcomes for this unit are to know some basic sorting algorithms just because they're very well known, and I don't want you to embarrass yourself by not knowing them, or at least I want to not be responsible for you not knowing. And you should know a little bit of the performance characteristics, how they differ, when they make sense to use. More importantly, we'll talk about a lower bound. So that will be the first case where you see the real utility of having abstract mathematical models for our computation, namely that we can prove impossibility results. I always like to compare this to a little bit what physics and engineering in the mechanical engineering would like to have but don't really have. We can prove impossibility results, something like the thermodynamic laws or conservation of energy or something like this. So where everyone is convinced it's not possible to convert energy without some loss. So if you say have a wind turbine that creates electricity, there's something lost on the way in terms of heat and friction and so on. That's something that engineers also know. The difference is in computer science, we can find lower bounds that we can also achieve. So we have a really small gap between what's known to be not possible and how close can we get to it. And I think engineers usually can only dream of that. Any combustion engine is still far away from the efficiency that would be the limit of energy preservation. There's so many things before that stop you from getting better. And so in a way, that's a really unique feature in computer science. It's engineering on one side, but also matching lower bounds for some problems. That's unique and quite fascinating. And the real reason why I think mathematical models of computation are so useful for the practical applications of programming and algorithms. All right, that was a long teaser for this one. We'll also then see how you can sometimes circumvent lower bounds by going out of the model. Another interesting thing. And we'll look at some practical bits, the Python sorting algorithm, and a little bit on dynamic programming, just very briefly in general. So a bunch of sections. We'll start easy today, work our way through. Before we go into any detail, I want to motivate a bit why we study this fundamental problem. So in a way, sorting is about the easiest to explain. So you have a list of things and you want to bring them in order. It's very easy to explain to anyone, even if they have never programmed. On the other end of the spectrum, it's still an open problem in that sense. If I ask you what's the best sorting algorithm in terms of the worst case number of comparisons, we still don't know. And by and large, the last real progress on this question predates most computers. It's from the 1950s. And since then, only very small bits have been improved on this. And so we still don't have a fully satisfactory answer for that. So that's kind of intriguing. More practical motivation is that sorting is used as a building block in other things. We'll see some examples. It just often happens. You've seen it just in the data structure section. Having an invariant that things are in order makes life easier because you can rely on more properties, and bringing things in order is sorting. We'll also use this a bit as a playground, but that's a weak excuse to torture you for so long, I think. We'll this is moved to unit 5. That slipped my attention. It'll have three parts. First, some of the basic bits. And I want to formally say what I mean by sorting. We've seen arrays before, so not too much to say about them. The examples will, I think, always have numbers, but of course sorting is more general. All you need really is a total ordering relation. So this is mathematically well defined. For us, it's fine if you just use the intuitive meaning. You have some way of telling which of two things is smaller. In Python, the way to write this is just this less or equal operator. Note that you can override this for custom classes. So you can define your own types. You can define new classes, and you can implement this special function with a double underscore. And then if you type in your program the less or equal operator for your custom objects, it will just call this function. So you can even implement this ordering relation for new kind of data types that you invent. Java has a similar means, not quite as elegant in the syntax, but achieves the same thing with the comparable interface. The goal, of course, is to get the array sorted, but what do we mean by this more precisely? We want to keep the same elements that we had in the list before. They should still be in the list afterwards. Kind of an obvious fact, but if if you don't add that, I could just zero out the entire array and say, yeah, it's sorted. No, we want the same elements in the array, but so that they're ascendingly sorted. I'm usually careful to put less or equal. It's not forbidden to have duplicates or have elements that are equal, that compare equal. Where in the syntax of this operator, x can be less or equal than y, and also y is less or equal than x. So in that sense, x and y are the same. Why am I stressing this? It's not necessarily the case that x and y are exactly the same thing. It could be objects. Say you have a list of employees and you sort them by their last name. By and large, that's unique, but not entirely, right? There might be several people called, I don't know, Muller or was it Smith? There's names that are a bit more common depending on the country, and then you want the people still to be different, even though they have the same last name. So this is a distinction between comparing equal with this lesser equal and being the same thing, being the same object. Okay. Well, for the experts, we'll look at internal sorting, but that's not too relevant. Again, my check for you is a question that you're not supposed to know the answer if you haven't seen this before. But the question is almost purposefully ambiguous. If you start asking these kinds of questions, that's probably the signal for me that you've seen something. If you want, say, what's the complexity of sorting in the comparison model in the worst case? All right, I see a big blob for Big O fan. n log n, pardon me. Yeah, I think this was I can't show this list of answers with the actual counts. Now the other trick is, should the answer to this question be theta or big O or something else? Let me leave it with that. I think the guess again is around half of you know this already. Maybe a few more, maybe a few yet more who just don't remember yet. So same problem, same game as before. We're in the territory of going through something that many of you have seen, but not all.